So, and you can imagine, try computing a surface integral on either one of these surfaces after coming up with parameterization for it. It'd be too painful. Even I wouldn't give an exam problem like that. Really. But the curve can be quite nice. Okay. Now, let's look at another example involving Stokes' theorem that goes the other way. Okay. So we have curve C, and it's the intersection of a cylinder, x squared plus y squared is equal to 9, with a plane x plus z is equal to 5. So what we need to do is, so we're going to have this ellipse type object that marks the intersection of a cylinder with the plane. And we want to compute the line integral of this vector field, and f is xy to z 3y. All right. Now, we could try to come up with parameterization of this curve and compute the line integral over it. But what we could do instead is apply Stokes' theorem. And so here is the curve C, and here is the surface S. So kind of like a so it's some ellipse hanging in space, and we're going to integrate over the interior of the ellipse rather than just the boundary curve of the curl of F dot product with N. Okay. So there's two things we need to do before we can do this. First, we need the curl of F. So that's going to be derivative with respect to x, derivative with respect to y, derivative with respect to z, cross product with xy, 2z, 3y. So we're going to compute this cross product.
What about in your notes at the very bottom of the page of the beginning? It has curl f dot ds.
Oh, okay. There's two ways of writing it. So we can also write it as curl f dot ds, the vector symbol, but that is equal to this. No, notice how there's the s bold there for vector. Yeah. So there's two ways of writing it, but this is the way that helps you evaluate it.
I feel like you're having to tell me everything once.
Well, that's what I asked earlier too. So.
Yeah. Yes, but I already know how allergies are affecting you today, so I'll give you a pass. Okay, so we compute the cross product. So we're going to have derivative with respect to y of 3y, so it's going to be 3, minus derivative of 2z with respect to z, so it's minus 2. And then here we have derivative with respect to z of xy, that's 0, minus derivative with respect to x of 3y, also 0. And finally, we have derivative with respect to
Someone's out there making noise in the hallway.
oh.
It's a warning sound.
Okay, so derivative with respect to x of 3y, to z, which is 0, minus derivative with respect to y of xy is minus x. I believe I have x in the notes. So it should be minus x.
That's a point, right?
But I caught it.
Oh.
Alright, I could give myself a point, but
And donate.
but not sure what the point would be of that.
Yeah, you're really so well in this class.
Alright, so that's one thing we need. The second thing we need is to parameterize this surface. So what we have here, on this surface, we have, it's a plane x plus z is equal to 5. So z is equal to 5 minus x for whatever x is, no matter what. The second thing is, we're within the cylinder, so x squared plus y squared is less than or equal to 9. It's equal to 9 on the curve, but we want the surface. So that's why we have less than or equal to here. All right, but every point on this has to satisfy this equation, because we're taking a portion of a plane. That's why I'm using this. All right, so the way we can parameterize this surface is as follows. We can let x be equal to u cosine v, y is u sine v, and z is equal to 5 minus u cosine v, 5 minus x, where u runs from 0 to 3, and v runs from 0 to 2 pi. All right. So now, what we need is the okay. We need to compute the normal vector to this surface. So for that we need partial derivatives of our parameterization with respect to u and v. So we have Ru, so that would be cosine v, sine v, minus cosine v. And then Rv is going to be minus u sine v, u cosine v, and then u sine v. And now we need to take the cross product. What we're going for is the integral from 0 to 3 in u and 0 to 2 pi in v. And then we have curl of f at r of u and v, dot product with the normal ru cross rv, dv du. That's what we're going for. We just got to fill in all this. So we need the cross product of these two. So we're going to have u sine squared plus u cosine squared, that's u. We have u cosine v sine v minus u cosine v sine v, that's 0. And then finally we have u cosine squared plus u sine squared, that's u again. Okay. So at least our normal has a nice simple form. And then we need to take the dot product of a curl with this normal vector. So curl of f, r of u v, that's an r, dot product with the normal is equal to 1, 0, minus x, so that's minus u cosine v, dot product with u, 0, u, so that would be u minus u squared cosine v. Alright, so that's no longer a vector. Okay.
And you have positive u cosine v.
In the notes?